First talk is dipolar stabilized first and second order anticycrimons in ferromagnetic multilayer. Timo Schmidt.
Okay, that is basically close. Ready?
Yes. Yes.
Thank you.
You have 30 minutes. Okay.
Okay, so let's start. Welcome to my talk, everybody. I will quickly introduce myself. My name is Timo Schmidt, and I'm at the University of Augsburg in Germany in the group of Manfred Albrecht, looking for spin textures in magnetic materials. Normally, Manfred Albrecht would give this talk to you, but he unfortunately couldn't come, so I'm taking his place, and I'm glad being here. And the topic today will be dipolar stabilized first and second order anti-skyrmions in ferromagnetic materials or multilayers. So let's get on with the motivation. Like the motivation for everything skyrmion based is basically since 2008 or 2009 the racetrack memory. And you could imagine that if you had a material where you could stabilize skyrmions, you could build a racetrack memory where you can say if a skyrmion gets by the detection, then it means a 0, and if no skyrmion gets by the detector, that means a 1, or the other way around. Doesn't matter really much. But the problem with that approach is that that the distance between the skyrmions, which would act as a 0 or a 1, is very volatile to pinning and other thermal fluctuations. So it would be a better approach to use different spin textures, like, for example, in this animation, an anti-skyrmion as a 0, to get this distance between the individual particles right. But for that, you would need a material that can host both skyrmions and anti-skyrmions under the same conditions. Another thing that is like holding racetrack memories back is obviously the Hall effect, which deviates the skyrmion when it's driven with a current that is spin polarized in one direction. So it could annihilate at the edge, and we don't want it. But we can also use that skyrmion Hall effect to our advantage, for example, in these skyrmionic interconnections, where you could say that these particles with no topological charge, so no skyrmion Hall effect, could travel straight through, and these other spin textures with a negative or positive spin Hall effect, spin Hall angle, would move to the sides. And that would have the advantage that you didn't need one connection for these textures and one connection for these, but you can have a shared connection, which would, you would need less connections and less material, obviously. And the last point is coming up recently. Skyrmions can be used for unconventional computing, to be more precise, for neuromorphic computing, where you try to mimic the function of a human brain. And there has been applications proposed that can act as neurons and ones that act as synapses, both with skyrmions. And you could also, with that approach to computing, could potentially solve a really important issue in computing right now, namely the von Neumann bottleneck, which is the problem that at the current von Neumann architecture, you have a processing unit and you have a memory unit, but they are apart from each other, so there is a time limit at how fast you can exchange information between these two. But with skyrmions, where you can have these processing units and also skyrmions for memory units, that could possibly be overcome. So let's get on with some previous work on skyrmions and basically anti-skyrmions. There has been a lot of research on skyrmions. Obviously, the research kind of exploded after they were found, but not so much on anti-skyrmions. Anti-skyrmions have been stabilized in these Heusler compounds with their symmetry of D2D. You can see here some Elton pictures of these spin entities, which are really well aligned in that lattice. And another, oh, that was the wrong key. And another example could be in Schreiber side with S4 symmetry. And in these materials, the skyrmions are stabilized by the Gialushinsky-Mourier interaction mainly, the DMI, and also through its really, and through its symmetry reasons. But we took kind of another approach with our anti-skyrmions. So this is basically what our system looks like. It's a ferromagnetic multilayer consisting of iron and gadolinium at very low thicknesses for each layer. And if you imagine that if you sputter such a system, then you can say that it's more of an amorphous alloy than really a multilayer. So that every iron has enough gadolinium partners nearby to get this ferromagnetic interaction. And it's also gadolinium dominant. We orientated ourselves for that at the works of Montoya et al., which you can see here, and this group worked on this iron gadolinium 80 multilayers and tried to stabilize Bloch skyrmions by the dipolar interaction. So no DMI interaction, but dipolar stabilized skyrmions. And I made this phase map, which shows the saturation magnetization and the uniaxial anisotropy. And there are a few regions here. So in the first region, where it says Q is greater than 1, Q is our quality factor, which is defined by the uniaxial anisotropy divided by the shape anisotropy. And because the shape anisotropy scales with the saturation magnetization, this is like a parabola kind function. And for these values, we don't get skyrmions. So we want to have a greater shape anisotropy than uniaxial anisotropy in these films. And also for that region, they found that they had, in the green, they had a skyrmion lattice, and for the blue dots, they had isolated skyrmions. So also the value of m squared over k to the power of 3/2 is important in that case. And we recreated that, basically, to get ourselves dipolar stabilized Bloch skyrmions, which have a rotational sense. And now the approach was, what happens if we stuck iridium layers inside the top and the bottom? Like we made a few samples with different numbers of iridium layers, because iridium has a really strong spin-orbit coupling, and it basically introduces DMI to the system. So we have a Bloch-type characteristic from our iron and gadolinium, and we could have this Neal skyrmion characteristic type, because in the DMI systems, most skyrmions form for a Neal type. And then the question was, if we get this Bloch rotational sense combined with a Neal skyrmion, can we get this anti-skyrmion spin structure, which is basically just Bloch domain walls separated by Neal domain walls. And I wouldn't be standing here if it didn't work, so I'm going to show you the results we got. One point, all of our samples were sputtered on silicon substrates and also on membranes, so we had the ability to transmit an electron beam through it and do Lorentz TEM microscopy on that. So on that picture we got a lot of things, so let's start with this one. That is a white dot with a black circumference, and it represents a counterclockwise Bloch skyrmion. That was already, yeah. So at the top, you always see the picture of the real thing, and on the bottom, here is the spin structure we would expect from such a spin object, and in the middle is a simulated Lorentz TEM contrast, which is basically just a really easy Python program that calculates how an electron beam, if it would propagate into that texture would be deflected. And in that case, this Bloch-Skyrmion would act as a focus lens. So the electron beam would get focused in the middle and leave a black circumference around it. So that is a Bloch-Skyrmion, these white dots. And there are also black dots, which is a clockwise Bloch-Skyrmion. So it's the same principle, but this time it acts as a defocus lens. So we get a black dot and a white circumference in the middle, and also that matches really good with our simulation, or our experiment. The next thing we have here is a bubble, a type 2 bubble, we call that. And that differentiates itself a little bit from the other objects. So this is an object that is not topologically protected in that sense. So you could have a uniform transformation to get that into the saturated state. So it's not topologically protected and not that stable. But also here the simulated picture really fits the measured one really well. Now we get to the interesting part. Here we first have our first order anti-Skyrmion, let's call it that. And we saw that contrast earlier. We have here these 4 block type walls, up, down, bottom, and right, divided by these Neal type walls. And you can imagine that in this direction, it acts as the focus lens from here. So you get 2 bright spots, and from up and down, it acts as this kind of rotation. So we get these dark spots. So like a cross from a white and a dark spot. And we wouldn't call it first order anti-Skyrmion if we hadn't have a second order, and we are really proud of that because that is, to our knowledge, the first time that thing was experimentally measured. And it basically behaves as a first order anti-Skyrmion, but it has one more iteration of a Bloch and a Neal type domain wall. So you get this radioactive sign, if you want. So yeah, that are the different spin textures we could stabilize at also the same conditions, like at 260K for 2 iridium layers inserted in that. Now let's see how our hysteresis loop is connected to the spin structure formation. The first thing we see here in the hysteresis loop is that the in-plane loop saturates faster than the out-of-plane loop, which is expected, as we said, that our shape anisotropy, which lies for a thin film in plane, should be greater than our uniaxial anisotropy. And so that is that. And another thing you often see at Skyrmion samples is this small opening at the out-of-plane hysteresis loop, which comes from that the nucleation and the annihilation of Skyrmions is an irreversible magnetization process. So if you go from zero field up to the saturation, you get another way, let's say it, than if you go down. So let's go that way. At zero magnetic field, we have here really tight labyrinth domains. If we go further up, okay, thanks. So if you increase the magnetic field, then you see that the periodicity of the stripes gets smaller, and you can also make a distinction between these big black and big white domains and the gray domains. And the white and the black domains are basically the ones with chirality, and the gray ones don't have chirality. And you can also in the picture see first Skyrmions forming. If you increase it further, we can see now that the trend continues. Basically, we have some Skyrmions, and that was it. So then we increase it further, and now all of the domains, of the stripe domains, have been broken apart into a lot of bubbles, a lot of skirmions, and also some anti-skirmions here, here, and here. And because we know that our bubbles are not topologically protected, they are also not that stable in front of a magnetic field, so another increase lets them vanish almost completely, or completely, I guess, in that sense. And only the anti-skirmions and skirmions remain. At the next step, if you increase it one step further, is that also the anti-skirmions annihilate because they are not as stable as skirmions. So we can translate that into some stability ranges. Our bubbles have the lowest stability in this range, around 100 milliteslas of magnetic field. Our skirmions have a wider range, are quite stable, and our anti-skirmions are a little bit more, so they go until there, are a little more stable than our bubbles, but not as stable as the skirmions at all. And this trend also continues, so our anti-skirmions of second order are less stable than our anti-skirmions of first order. And I also brought you a little film to see it with your own eyes. So we increase the magnetic field, and you see that the domains get bigger, and there are some skirmions here, here, here, and now everything breaks up into bubbles. The bubbles disappear. There were anti-skirmions for a second, but I couldn't talk fast enough. And after that, we are in this situation, and everything annihilates. The picture is a little bit shifting. That is because if you excite the system with a magnetic field in the Lorentz stem, the beam also gets a little bit shifted. Yes. But that for the experiment, and our friends from Vienna, thank you, Sabri, also did some micromagnetic simulations for us with these parameters. And I also have a film for that. So we have a little bit more zoomed in picture of our structure. And we can see these walls getting smaller. And I guess here are round particles forming. And you then can see that like all of the stripe domains break up into bubbles eventually, like somewhere around here. And then the bubbles disappear because they're not really stable. Then the anti-skirmions. You can't really tell the anti-skirmions, I guess, from that perspective. But the skirmions are the most stable, and they stay there until it is almost saturated. So a really good a good fit to our experiment, let's say that. So let's talk a little bit about the nucleation of anti-skirmions. Because we noticed like a trend for these nucleation sites and why they nucleate. And the trend is that they often nucleate at sites where 2 or 3 domain walls meet each other. And you can see such an incidence here. And this is one domain wall, this is one domain wall, this is one domain wall, and this is basically a Bloch point. We're at 76 millitesla for that. And if we increase the magnetic field, you can see that this domain wall detaches from there and leaves this there. And another increase in magnetic field shows that another domain wall will lose its grip on that structure. And you can almost see a full anti-skirmion here. And with another increase, we are basically there. And we've seen it a lot of times at different spots where these 3 domain walls meet and an anti-skirmion comes out of that. But we have to experiment a little bit more to qualify that, really. But also we have simulations for that, which also show a very similar picture for this formation of an anti-skirmion. Good. So now we have a little bit of an anti-skirmion recipe, let's call it. So Montoya et al. Did their phase map, and we thought let's do one ourselves. So we have here this region where Q is greater than 1 or Ku is greater than K shape. So that is basically forbidden area, and we can then just transfer that data from Montoya et al. So these are only skirmions, so no anti-skirmions in their films. And if we add our own, so then we have here like these coexisting anti-skirmions and skirmions in violet, and the skirmions, like samples which only had skirmions, in the blue squares, and also in plane domains, like basically here where the Ku value is just too low to get these out of plane things. And with a little bit of simulation data for these stable anti-skirmions and stable skirmions, also from our friends from Vienna, we see that this phase map also agrees very well with the experiments. And yeah, so that is basically the recipe to get anti-skirmions. You have to somehow get in that phase pocket. But the question is, okay, we can make our samples so that they have this this value of uniaxial anisotropy and saturation magnetization. But is there a way, for example, if we make a sample and we see, okay, it is up here, like 40 kilojoules per cubic meter and 200 kiloamperes per meter. So we would be out of that pocket. Is there a way to do that after deposition, to somehow shift that like down or to the side to get into that phase pocket? And the answer is yes, we try to do that with local post-deposition anisotropy engineering. And the idea with that is that we irradiate our films with helium ions. And you can see from that MFM pictures that before irradiation you have your labyrinth domains you would expect from your films. And with a higher dosage of these of the helium irradiation, you get a little bit more fuzzy here, and at 10 to the power of 15 ions per square centimeter, you are just so in plane from your irradiation that there are no more skirmions or stripe domains forming. So basically also for this labyrinth domains you need a little bit of competition between those in-plane and out-of-plane moments, and you destroy that with ongoing irradiation. So that is really an in-plane film. And the next thing was the local part. So what we did was we took our iron gadolinium multilayers with the iridium, and we tried it with nanospheres. So these nanospheres, we have had different sizes of these, and they were between 200 and 800 nanometers. And we put that in an aqueous suspension, and then evaporated this aqueous suspension so that the nanospheres could align on that multilayer really neatly. And we got a picture of a SEM here, which shows that they really form a really good hexagonal lattice. And the next step would be to irradiate it with helium ions. And you can guess that the helium irradiation can't transfer through the nanospheres, so it only gets in between the nanospheres, and you only destroy it like that, your area where you don't have your nanospheres. And then if your nanospheres are approximately the size of your skirmions, then you basically have a hole where these skirmions can form in. And out of that hole, there are like forbidden regions for them. And so we can remove the nanospheres and then look at it with the MFM, and we really see some round objects here, almost in a hexagonal letter. It gets a little bit confusing around here, but there are areas where you can really see that hexagonal lattice from the nanospheres. Looks like it's working really good, but there are some problems with this technique. At first, from that picture, we have no insight like on what spin object that is. So this could, like the MFM is only sensible to the out-of-plane magnetization, so this could be skyrmions, this could be anti-skyrmions, this could be bubbles possibly. So we don't know. The better approach would be to make this kind of experiment on a membrane and look at it through Lorentz TEM. But the removing of the spheres in precisely damages the surface. So this is a picture of a sample that has its nanospheres removed, and that is not an MFM picture. This is a height picture. And so you can see where this nanospheres was and were, and there is approximately like 3 nanometers of film they just rip off when they get removed, because they like glue a little bit to the sample. And with membranes, for membranes, it's not suitable because you would damage your membrane and you wouldn't see anything. So the question is, can we realize it another way? And now comes the outlook. We could do that on membranes with focused ion beam ionization. We have made some experiments with that, but one are not really far. But the idea is basically if we irradiate parts of the sample where the skyrmions shouldn't be, and we leave parts unharmed where they should be, then basically the skyrmions should only be allowed to enter that part or be in that part of the sample. We could do some things like these artificial racetracks, where you don't need like nano strings, but could use it that way. Or what you can also do with that is something like that, where you have these hexagonal irradiated regions, which leaves these crossings where the skyrmions can meet, or the stripe domains can meet. And as we have seen, like that anti-skyrmions are more common to nucleate from these crossing points of the main walls, we could use such a structure to get more in detail about the nucleation of anti-skyrmions. And another outlook thing would also be, we have found now anti-skyrmions of our first order, and we have found anti-skyrmions of the second order. So what about higher orders? Like, these are simulated pictures, but could something like a third order anti-skyrmion or a fourth order anti-skyrmion exist? Yeah. And that's basically it. So I hope I could pique your interest a little bit in the research we do in the University of Augsburg. And now I would be open for questions. So thank you very much.
Thank you. Questions or comments? Yes, please.
Very nice work. I really enjoyed it. Thank you. One question, maybe I missed your explanation. What's the mechanism for stabilizing such anti-skyrmia? I saw usually you need some asymmetric DMI.
Yes, but in this case we are dipolar stabilized. So we also measured the DMI strength. Wait. There are a lot of animations. So yeah. I skipped a part also a little bit. We also measured the DMI. Our anti-skyrmions and skyrmions are dipolar stabilized, basically.
So it doesn't invoke any asymmetric DMI in this case?
Well, I guess not.
Okay.
For the stabilization, not.
Also, I remember Eric Fullerton was telling me in that system they saw 3D structure. So like in the middle, there's a block skirmion, and then there's neo cap on top and bottom. Do you see any depth-dependent variations of the spin texture?
Could you explain it a little bit? I guess not.
So their system is without this iridium, it's just the iron gadolinium, and they saw, typically you see the block skirmion, but there's neo cap. So the top and the bottom, there's a different configuration. I wonder whether you see any depth-dependent variation in your film.
Well, I guess we have only measured like Lorentz stem, and you are not like height sensitive with Lorentz stem. So I don't know, actually.
Okay, thank you.
Yes, please.
Thank you. So you're saying that skirmers and anti-skirmers are stabilized by dipolar interaction. So I don't really understand what is the role of iridium, because you're saying that it introduces DMI, but in the end, they're not DMI due to DMI.
In the end, it's it introduces DMI, but wait, just the wrong direction. Sorry. We thought that it would introduce more DMI, but it effectively said. Reduces the saturation magnetization, which was also like a point from getting like somewhere here, where Montoya et al. Were, to getting into that phase pocket.
But why does it reduce the magnetization? I don't understand, because the iridium. Yes.
We are also not that sure. It could be that I read that iron, the iron and the iridium could like couple, or they. Yeah, I'm really not that sure about that.
I don't think
but
there is a strong induced moment on the iridium. So
it definitely reduces the saturation magnetization, because we had like films without them and with some iridium layers, and the saturation magnetization goes down. What the reason for this is, I'm not that sure, but yeah, basically we don't have DMI as we expected it. I hope that somehow answers.
Yes, please.
Okay, thank you. Maybe related to the same question. Are you sure that you can change the saturation magnetization without changing the DMI, and that you get anti-skirmions without DMI? Like it seems to be there.
I guess we have such low DMI that it can't be a stabilizing factor, and that the dipolar interaction in our films is the main factor for this stabilization, yes.
Okay, and then DMI and saturation magnetization here are two independent parameters, or anytime you move one, you move the other?
I guess they're fairly independent.
Okay, thank you.
Yes.
Thank you very much. Thank you very much.
Second talk, the last talk before coffee break is Sikrimon device integration. Felix Butner from Germany.
Okay, can you hear me?
Yeah.
Okay, good afternoon, everyone in Turkey. Thank you very much for this invitation, the kind of introduction. So after these two beautiful talks on skirmion fundamentals, my talk will be more on the applied side, how we can control skirmions for device integration, especially how to achieve deterministic and ultra-fast creation, annihilation, and propagation of magnetic skirmions. And throughout this talk, you will see a lot of the images like this, where a skirmion is depicted as a black circle, and it's usually integrated into some nanostructure, like a track of magnetic material, and along this track we can inject current pulses, we can apply all kinds of excitation to that. So when talking about applications of magnetic skirmions, what do we have in mind? There are a few examples I would like to show here. The first one is, of course, data storage. The most promising application, or most known application of magnetic skirmions is the skirmion racetrack memory. But data storage, as shown here, But data storage can be much more simple. For example, as representing the numbers of the count event just by the numbers of skyrmions in the device. And that can be used, for example, for embedded memories, which operate at very low energy consumption. Skyrmions can also be used for sensors. For example, they react to a magnetic field in a very fast way. And this can be used for sensors required in power electronics, in navigation, in medical applications, and so on. And then skyrmions have also intriguing behavior, including some fading memory and connectivity, which might be interesting for realizing neuromorphic computing devices. And all of these applications have in common that it requires a nucleation, usually also propagation, and ultimately also annihilation of skyrmions. Typically also on a relevant time scale, and of course with a deterministic hash. There's also a problem of readout, which I will not be addressing in this talk. So the first part is about nucleation. How can we nucleate skyrmions? And the question is kind of tricky because it usually starts with the question of if skyrmions are topological objects, how can we then transition between the topological object and the non-topological ground state? If this is topologically forbidden. Well, the question is simply answered by considering the skyrmion live on a discrete lattice. So the topology of the skyrmion, instead of being considered as a sort of, for example, donut shape that you want to transform into a sphere, you should rather consider it as a chain like this here, which has a link where you can open and close the chain. And this is also illustrating the fact that you can brute force, of course, create or annihilate a skyrmion, which costs a lot of energy. But if you have the correct handle, if you know how to open and close this chain on this position here, then it can be relatively easy and done with low energy. And for this particular talk, I will focus on two device-compatible mechanisms that allow such nucleation in a fast and deterministic manner. The first one would be spin orbital nucleation, and the second one would be laser nucleation. So for the spin orbital nucleation, we need two ingredients, basically. The first one is vertical inverse symmetry breaking of the material. So in this case here, you have a superstructure where you have at the first layer, you have a heavy metal, can also be a topological insulator, where you have strong orbital interactions. And on top of that, you have a magnet. And then the third layer would be a different material. It's not magnetic, but also not the same as the one below. So this gives you inversion symmetry breaking that gives rise to this spin orbit torque and also to the gyro-Maria interaction in the material. The second ingredient you need is then lateral symmetry break. So if that film is uniform, you will be it will not produce any skyrmions when you inject the current. So you need some inhomogeneity in lateral directions. So that can, for example, be a defect where locally the magnetic anisotropy is reduced. You can also change any other micromechanical parameters just locally. So this is now here showing X and Y dimension of that strip, and here in the Z direction the anisotropy. So if you combine this and then inject the current pulse of a exceeding a certain threshold amplitude, then you will see that you will actually switch locally the magnetization from up to down near that defect here, where the necessary in-plane field provided for this spin orbit switching is provided by the gyro-Maria interaction. You can then by applying continue to apply this current pulse, move away this locally switched area, which is not yet a topological object, but is rather like just a magnetic bubble. You can move that away from that defect, and ultimately once you switch off the current, because the energy of this defect here is so high, it will transform itself into a magnetic skyrmion. And this mechanism is quite universal. It has been studied by many groups, even a lot of them before our publication. And it's not limited to an orbital generation, but it also can also be seen in spin transport. So essentially, the key behavior here is. Oh, actually, let me go to the experiment first. The experiment shows that we have indeterministic deviation of magnetic skyrmions above a certain current threshold. So here we plot the current pulse length and the current density, and the phase diagram resulting from that is that we have above this line here, we have deterministically skyrmions, and below that line we have deterministically no skyrmions after applying the currents. And interestingly here, you can generate skyrmions with current pulses below a nanosecond, and at quite reasonable current density. So that's all device pattern. And the exact function that follows here is very similar to identical to the one that you observe for spin orbital switching, uniform spin orbital switching as an MRAM technology. So this is quite well understood. And in the experiment, we can also do imaging, and we see that if we synthetically generate a magnetic track where we have a constriction, and that constriction is breaking the inversion, is breaking the lateral symmetry. So this is the point where the skyrmions can then nucleate. Indeed, when we inject a current pulse, we see that skyrmions nucleate from one of those corners here. We can move them away by further current pulses. We can also nucleate skyrmions on the opposite side of that constriction, and again move the skyrmion away from that point. So that's a viable way of nucleate skyrmions in a raised memory. It is fast, so it's happening on a nanosecond timescale, or even some sub-nanosecond timescale, and it is defect-driven. That's an important point here. So you need this lateral symmetry break to nucleate skyrmions. Quite differently from that is the phenomenon of laser-induced nucleation. So there's a number of differences, but I want to highlight two. The first one is that if we illuminate an initially saturated magnetic sample by a single femtosecond laser pulse, we get a entire array of skyrmions, get hundreds or thousands of skyrmions after that laser pulse. So we have a very high density after just one pulse. And if we plot the distribution of these skyrmions, so we repeat the experiment over and over again, we plot and we overlay all of these images, we see a image looks like this one here, where we identify that more or less the distribution of these resulting textures is random. So the remaining variation that we see here is just short noise. So this is a homogeneous process. It does not require defects. And if we look at the time scale of this, we can actually do that at the European Free Electron Laser, and the experiment is like that. We put our sample into the X-ray beam. We initially start with a sample that is saturated, then expose it to a laser pulse, and then to an X-ray pulse. And the X-ray pulse is then scattered from this resulting state here and detected on a detector in the far field, and by that recording the Fourier transform of the magnetic pattern here. And we learn a lot of things from this experiment, but the main thing I want to illustrate here is that we see when this process has finished. So we see when the total intensity of that scattering distribution here has saturated to its final intensity. And we see that this happens actually in 300 picoseconds. So this process is very fast. So remember that even the simulation that I showed before for spin orbital nucleation took about 6 nanoseconds. In this case here, for a single skyrmion, in this case here, we are nucleating hundreds of skyrmions in only 300 picosecond duration. So this process is even faster than current reduced nucleation. And importantly, it does not require any defects in the material. So we just illuminate the homogeneous material, and we still get skyrmions out of that. Now, how can we make both of these processes then deterministic in terms of where exactly to nucleate the skyrmions? And one of the answers is we can use helium ion irradiation. And so this is shown here, where we have a magnetic track And the upper part of that track is irradiated by helium ions. So to locally reduce the anisotropy of the material, the lower part is not irradiated. And what we see is, if we then inject a pulse, we nucleate skyrmions exclusively in the area that has been irradiated by the helium ions. So this is kind of the way that I also explained before for the spin orbital nucleation of skyrmions, where in the area of where you reduce the anisotropy, you get skyrmion nucleation. You can also do that in line shapes. You can have a line of lower anisotropy or irradiated by helium ions. You can have dot arrays where you really produce skyrmions only in dedicated dot positions. And interestingly, this also now works for laser nucleation in a certain range of magnetic fields. So in this case here, we expose the sample by a femtosecond laser pulse, and what we observe, the skyrmions also then appear exclusively in these areas which we have irradiated under a certain range of magnetic fields. For the laser-induced nucleation, we can also focus the heat of that laser to certain areas, and that is also similar to previous reports where people have used a tip of an AFM or plasmonic effects. And here we are showing that you can also use backside reflected masks for tuning where exactly you deposit the heat of that laser. For example, if you start with the sample that has a magnetic film here and a transparent layer on top and a metallic layer behind, then in that case, you have matching between the magnetic layer and the metallic layer, so that there is more light being transmitted and less being reflected at this interface, and more being reflected at this interface. You know, when you have a metallic film, the metal to air interface is quite strongly reflected, so the metallic film usually looks like a mirror. And in that case here, when you have more mirror effect on this part of the material than on this part of the material, you actually see that you expose this here with a high fluence scheme. You see that you get skyrmions everywhere. Essentially, you overcome this threshold for skyrmion nucleation everywhere. However, at low fluences, only the part where you have reflectance on the backside is then heated above that critical temperature, whereas the part that is where you have the favorable transmission of that light and less reflection is heated less, and you get less skyrmions. You can actually do it also funnily the opposite way around. You can put the magnetic film, then a transparent layer, and then a metallic film, and now this interface here between the transparent layer and the next metal layer is acting as a mirror, whereas the transparent layer and the interface to air is producing less reflections. So in that case, you have the exact opposite. At high fluences, you can produce skyrmions everywhere. At low fluences, you produce skyrmions only in the outside of the material. You can use that phenomenon to nucleate skyrmions in a variety of patterns. For example, there's this grid shape here, or you can even use interference effects in this geometry here to produce skyrmions in ordered patterns by on the order of the wavelength light. Essentially, this is showing a concentric interference pattern between the incident light and the reflected light, producing these rings. So this is a means of achieving deterministic nucleation. Let me show you that this is not limited to femtosecond laser pulse, because obviously if we talk about applications, it will be very hard to integrate a femtosecond laser into a device. However, as other groups and have also reported, you can induce skyrmions by heat even on a slower time scale. For example, this report here has shown that you can induce skyrmions by Joule heating of the material on a time scale of a few nanoseconds. This experiment here has shown that if you put a heat element next to the magnetic track here, you can induce a transition from its drive domain state to a skyrmion lattice. So this is on a even slower time scale, and this is on a very slow time scale in a TEM experiment, where they heated a sample statically on a very slow time scale above critical temperature, and then cooled down. And what they see is when they actually exceed the temperature of in this case 650 degrees Celsius, they come back to a high density of Mexican scams. If they heat slightly below that temperature, they get to a state with very low scam density. Okay, now we have looked at the nucleation. Now what about propagation? So here I would also like to take two examples. The first one is magnetic field-induced motion, because this is interesting for sensors. Here the experiment is that we have a skyrmion containing disc. So this is a disc of a few hundred nanometers in diameter, and around that disc we put a microcoil to inject a field pulse, to generate a magnetic field pulse. This is a simulation of the geometry. So here is the current conducting microcoil, and it's producing a field on the order of a few tenths of millitesla at the skyrmion position. Here are the two skyrmions. And here's a time resolved video of what happens to the skyrmion state if we apply such a magnetic field pulse. And here you see that here's the shape of the field pulse, and you see that the negative pulse is producing a new domain here. That new domain is displacing that skyrmion, and upon reversal of the field pulse, the new domain is annihilated, and the skyrmion returns back to its initial position. And the entire duration of that video is 14 nanoseconds. So this is a very fast and deterministic response to a magnetic field pulse. Another type of dynamics is motion of the skyrmion over long distances, and that has been proposed especially by this paper of Albert Feld's group and others, that you can use in orbit torque to drive skyrmions very efficiently and very fast. And this experimentally has been realized in this paper here by group of Jeff Beach, where they have seen that you can actually drive skyrmions with velocities of 100 meters per second by, I would say, reasonable current densities. It has also been observed by the group of Axel Hoffman et al. Even earlier than that you can drive skyrmions with this means at very low current densities, but then also reach very low speeds. So in terms of speed, it's actually very interesting to note that the speed of skyrmions ultimately is limited. And this is something surprising, because in the original model by Thiele, so if you look back also at these graphs here, you would anticipate that actually the velocity scales linearly with the current density. And this is actually true up to a certain point. And when you drive skyrmions then faster, it's interesting to see that here the skyrmion data in black and the domain world data in orange, that above a certain velocity, you actually also saturate the velocity of the skyrmions. And this is surprising, because according to the Thiele model, where you assume that the skyrmions are a rigid particle that you just displace by the current, but not change the shape, the velocity would not be limited. So why is this so? So interestingly, the velocity is also limited in micromechanical simulations, and that's shown here. So this is a pure simulation plot. Initially, it starts linear with so this is the regime that's been measured before. So here, the velocity scales linearly with density, but ultimately it saturates to a velocity very similar to that of the main ball. And the reason being is that as you drive skyrmions fast, they ultimately transform into this shape, into shapes like this, which more or less look more like a pair of domain walls and much less like a rigid skyrmion. So the assumption that skyrmions would be rigid does not hold at very high current densities. So what we find by scanning a variety of different material parameters is that skyrmions actually never move faster than the main walls. So if you want, that's not too bad. As you see, the velocity that you can reach is still quite high, but you should consider that if you want to have a material where skyrmions move fast, you need to also realize fast main walls. That's experiment usually much more accessible. Now coming to the third part, annihilation. So here I propose a mechanism of laser-induced annihilation. And the reason is, let me show how this works. So essentially, when we start at a certain field in a saturated state, we reduce the field, and then we expose the system to a laser pulse. If the field is low enough, we would produce a skyrmion state. This is shown here. So this is a metastable saturated state that's transformed into a skyrmion state. Now what we find is when we increase the field of that same skyrmion, we expose it again to a laser pulse, we annihilate the skyrmion. So the hypothesis here is actually that the laser-induced dynamics always transform the system into ground state. Essentially, you heat it so much that whatever system relaxes to is actually the global ground state of the system. And if we plot here the energy of the skyrmion as a function of radius for various magnetic fields, we can actually analytically understand that at certain magnetic fields, the skyrmion state with a global ground state, if you increase the field or make it higher, then the skyrmion would be a metastable state higher than the ferromagnetic state at 0, but still separated from that ferromagnetic state by some energy barrier, so it would not annihilate on its own, but rather if you expose this to a femtosecond or to a fast laser pulse, it will actually be excited over the energy barrier and go to the ground state where there's no skyrmion. Okay, so we can actually use this to combine everything into one single device. So here we have a magnetic track, we can inject current pulse, we have apply a magnetic field, and we can apply a laser pulse. And we start with the empty state, where there's no skyrmion. We nucleate the magnetic skyrmion with the current pulse. We then move that skyrmion by further current pulses to the left and to the right, and then we annihilate the skyrmion again by a laser pulse. And all of this has been found at a constant magnetic field, so this is quite device compatible. Okay. With that, I would like to thank all the contributors to this work. This has been a combination of several papers. There's a lot of people involved here. I would like to especially thank Bastian Faul, Lisa Marie Kern, and Katika Gerlinger and Stefan Eisenberg from TU Berlin, and the Max Born Institute in Berlin. My postdoc supervisor Jeff Keach and co-workers Claire Kalitsis and Ivan Lemach, and also from my PhD work, that was the field-induced motion with Christoph Holz and Matthias Floy, and more recent collaborators in terms of theory, in terms of materials provided, and there was a lot of team time experiments. I cannot go into all the list of people here, but I would like to thank them very much for their contributions. So with that, let me summarize the outlook. So first of all, I hope I convinced you that we have now skyrmion nucleation, propagation, and annihilation quite well under control. We can actually nucleate skyrmions by spin orbital or current pulses or heat pulses, so we can produce from a saturated state, we can go to a skyrmion state. We can propagate skyrmions by magnetic fields or current pulses. We can annihilate them again by light pulses and integrate everything into a functional device. We can make this deterministic positioning by helium irradiation, and speed is on the order of picoseconds to maybe up to 10 nanoseconds. So this is all device compatible. So what is next? How can we actually now reach a higher technology readiness level? I actually encourage people to think beyond race-strict memory applications, not only because race-strict memory is kind of difficult to design, but also because there are, I think, better cases where skyrmion can make a unique contribution to a problem that is where there is no incumbent technology. So for memory, we have I think, quite good memories, but there's other problems in the world that have no technology solution yet. And for that, we also need to communicate better with industry, identify concrete needs, and define use cases. I think there's, again, a lot of promising functionality of skyrmions that can use for addressing actual problems that exist. We just need to identify what those problems are. And then solve the problem of non-invasive readout is certainly something that needs to be addressed, and solve the problem of temperature stability, meaning that the device should work the same way at minus 20 degrees Celsius up to 150 degrees Celsius usually. So that is another kind of engineering kind of question that needs to be addressed. Okay, with that, I would like to thank you for your attention, and I'm very open for questions.
Yes, thank you, Dr. Felix. Comments or questions?
Thank you very much. Could you tell us more about the mechanism leading to skyrminucleation with the laser pulses, please?
Yes. Wait, let me see if I have...
And connected question, I mean, what is the characteristic of your initial magnetic layer? I mean, you cannot nucleate whatever the magnetic parameters of your initial magnetic layers, I suppose.
Yes. So I think the best slide I have for this is this one. So the atomistic mechanism is essentially that we remove transiently the topological energy barrier. So the topological, if you here plot the energy as a function of skyrmion diameter, then the skyrmion would sit here in that energy minimum, and the energy barrier here is the one that goes from this state, the field polarized state at 0, to that maximum energy that is between this state and this state here. And this energy barrier here is 8 pi times the topological torch times the exchange constant times the film thickness. And the mechanism for annihilation, so the problem here is that this is on the order of several hundred kT at room temperature. So there's no way you overcome this by just random thermal excitation, even if you heat the system with the laser pulse. So the mechanism is different, namely that we actually reduce the effective exchange coupling by driving the system very close to the Curie temperature. Not over the Curie temperature, because there you have no order, but just below the Curie temperature, we find a phase where the exchange constant is very low, so you can have rapid changing of topological charge, because that energy barrier is essentially zero, but you have still enough exchange to produce a order over a few spins, enough to have a seed for a magnetic skyrmion. And then moreover, our layer system here also asks about the material. So the system here is a multi-layer of cobalt platinum, or in other cases platinum, cobalt iron boron energy. And this is a succession or a layer of magnetic and non-magnetic materials. And here what the laser is doing is it's also decoupling all these layers. Meaning that the dynamics in one of those is separated from the dynamics of the next one. And then you're reducing the effective layer thickness from the stack of the whole 15 repeats to the thickness of a single layer. That again reduces the magnetic, the energy barrier for skyrmion creation. So that's then essentially the idea of like how the path would be for that laser skyrmion creation. So you start at 0, and then you go without having to overcome that energy barrier to the skyrmion ground state.
Sorry, but in platinum cobalt multilayer there is no DMI.
That's true. And the hypothesis here is that we do heat the system from just from above. So transiently, we are actually inducing inversion temperature break. So transiently, the system is hotter on the top than it is on the bottom, and that heat gradient then produce a transient DMI that is leading to that skyrmion creation. To be honest, the atomistic simulation that is currently accessible does not allow to simulate a system like this, especially not of that thickness and not of not with the non-local straight interactions. So this is a kind of simplified model, but we believe on that transient time scale of a few tens or hundreds of picoseconds, that is what is driving the physics. We actually check that the resulting state is purely skyrmions. So by Lorentz TM, we check that even in that system, which has no DMI at room temperature, in equilibrium conditions, it has the laser produces a state of exclusively skyrmions.
Yes. Any more questions?
Well, maybe just one comment that in principle, even though they are symmetric, there will be net zero DMI, but I think in realistic system, there's always defects, impurities, so they don't quite exactly cancel out. So there could be some.
No, that's true, but probably the DMI would be small.
That's right.
And we also like the resulting textures are blob type. So at equilibrium, they are not nail skyrmions, but they are blob skyrmions, meaning that the DMI contribution to the chirality is relatively small.
Yes. Dr. Büttner, thank you for your talk.
Okay.
Coffee break now.
Yeah. Thank you very much. Bye.
böyle iyi. Biraz şey gözüküyor. Dr. Behler, can you hear me?
Yes, everything's perfect.
Okay. Okay. Let's start. The first talk is for generation for neural network potential for metal simulation by Jörg Behler from Germany. We are listening to you. You can start.
Thank you very much. It's a great pleasure for me to be part of this meeting, and I would like to take the coming half an hour to present your historical overview about the evolution of machine learning potentials. And I would like to use a classification scheme into 4 generations, which I would like to illustrate here using high-dimensional network potentials as developed in my group. So our goal is to reach an atomic level understanding of complex systems in chemistry and material science. We want to understand chemical reactions or materials properties. And for this, we need to run predictive computer simulations with first principles of ab initio quality. So if you look here at these typical systems like a slab with some molecules absorbed that can address in this idealized system here directly by electronic structure methods like dense functional theory, or this ideal unit cell of an FCC material, or here solid-liquid interface of a 1-1-1 surface in contact with water, or even a system like unit cell here of a metal-organic framework as a hybrid or organic-inorganic material. If you compare this with reality, here shown on the right by various imaging technique images, then you see that the reality is much more complicated. So you can have disordered surfaces, you can have large-scale defects like grain boundaries, you can have surface imperfections, and other types of defects in crystalline materials. And this combination of the need to describe very different types of bonding, which I would like to summarize as complex bonding, if you have to describe covalent interactions, metallic interactions, ionic bonding, dispersion interactions, all with a high accuracy, and at the same time large systems that often contains thousands of tens of thousands of atoms to model statistical structure setups here. This is making these simulations very challenging for theory. And the central role for all these simulations is played by the potential energy surface, because this potential energy surface contains essentially all information that we need. So we have global and local minima, so we get structural information, we can get derivatives of the energies of the forces to have dynamical studies and look at thermodynamic properties like free energies, for example. We have barriers or transition states that allows us to study chemical reactions, and we can also look, for example, at vibrations, so we can make contact also with experimental techniques like vibrational spectroscopy. And because of this central role of potential energy surface, the accuracy of the results that we get from computer simulations crucially depends on the quality of this potential energy surface. Now, so if you look into the toolbox of theoretical chemistry and material science, we find a whole hierarchy of methods starting from the very accurate wave function-based quantum chemical methods via density functional theory, and then by introducing more and more approximations to end up with very simple classical force fields. And this allows us to extend step by step the size of the system and also simulation time. But in the end, what we have to do is we have to make a compromise here between accuracy and efficiency of the simulations for the problem that we want to study. Now, and the question that now comes up is there a way to bypass this hierarchy and transfer the accuracy of the electronic structure methods, in our case mainly density functional theory, but can be also any other of these methods, to this order of magnitude here in terms of system size and simulation time that at least are comparable to these reactive potentials like the embedded atom method or the Tersov potential, which have been used for a long time in material science. And for this, bridging this gap, we want to use machine learning. And machine learning potentials are not new. So they are as almost a quarter of a century old. And you see here just some paper highlights of past 25 years in the field of neural network potentials and evolution. And you see here that the entries become denser and denser from the bottom to the top. So this is a very active field of research with many methods routinely now developed. But of course, there's more than neural network potentials. For example, Gaussian approximation potentials, spectral neighbor analysis potentials, moment tensor potentials, gradient domain machine learning, atomic cluster expansion, permutation, variant polynomials. So there are many different types of machine learning potentials which are nowadays very successfully applied. And to sort this a bit, for the case of neural network potentials, I would like to classify them here into four generations, depending on the types of systems and the physics they can describe. So the first generation of machine learning potentials is essentially identical to the first generation of neural network potentials, because at that time only neural networks have been used for representing the potential energy surface. And the first group was the group of Douglas Dorn at the University of Delaware, who suggested to use such a feed-forward neural network to construct a functional relation between the potential energy of the system and the structure, which is then described by several input neurons here. So it can be some form of coordinates describing the atomic positions. And the rest of the feed-forward neural network then just provides the mathematical flexibility to represent the energy based on a set of known reference data, and all these arrows here represent the fitting parameters, and they are trained iteratively to reproduce the energy of a set of known structures, and typically also the forces. And then once these parameters have been optimized, then the neural network can be used to predict the energy forces for similar systems, many orders of magnitude faster. So this first generation of machine learning potentials consisted of about 30 papers published by about 10 different groups. And as I said, all these works are basically based on artificial neural networks. Yeah, so a lot of mathematical advances have been made concerning the training of the neural networks, the exploitation of the symmetry. The systems have been extended to surfaces, and spectroscopic accuracy has been reached, and also the surface symmetry has been explicitly considered. So the basic ideas and the key concepts are well established, and they date back almost 20-25 years now. But there is a serious limitation for this first generation of machine learning potentials, and this is that they are applicable only to low-dimensional systems. This has several reasons. One is that you simply cannot make such a feed-forward neural network larger. So for each additional atom, you would have 3 more degrees of freedom, corresponding in principle to 3 more input neurons, and you would have to train at some point a very large network with very large training data sets, and this becomes impractical at some point. More severely, from a conceptual side, is that it was very difficult in the early times to include the permutation symmetry of the potential energy surfaces. For example, if you have a water molecule with two chemically identical hydrogen atoms, and you exchange the order of the hydrogen atoms, then you still have the same water molecule with the same energy. But since all these weight parameters here are different, the order of the input coordinates matters. So whenever you change the order of the atoms, you would also change the energy of the system, which you don't want, of course. Another thing why you can, for example, use Cartesian coordinates is that they, with their numerical values, depend on the rotation and translation of the system. Excuse me. And so whenever you translate the system by a few Angstrom, you change all the numbers, and then you get a different output of the feed-forward neural network. And then even if one can overcome all these problems, then the potential would be valid only for a given system size. So whenever you add another atom, you have 3 undefined connections to the network, and you could not use this potential. So this is not a general solution for all types of systems. And now this brings me then to the second generation of neural network potentials, which allow to use machine learning for very large systems, exploiting the concept of the locality of a major part of the atomic interactions. So in the end, this consists of 3 steps. The first step is to replace the single feed-forward neural network by a set of atomic neural networks, and each of these atomic neural networks provides the energy of a single atom in the system as a contribution to the total energy. So the total energy is the sum of the outputs of a set of feed-forward neural networks, and these atomic energies depend on the local chemical environment of the atom up to a certain cutoff radius, which is not so small, so typically 6 to 10 angstroms. And then the task is to describe the positions of all the neighboring atoms inside here by many-body descriptors as a suitable input, having all these invariances with respect to rotation, translation, commutation, and in our case we use atom-centered symmetry functions. Nowadays there are many other alternative descriptors available. And this is what such a high-dimensional network potential for a binary system looks like. For each atom, there's one line in this neural network. The color here represents the element. So the total energy is the sum of all the atomic energies, which are the outputs of the atomic neural networks, which are the same for a given element, ensuring permutation invariance. And then, as input vector, they get a set of atom-centered symmetry functions, which have all these invariances. And the symmetry function values in the end are obtained as a coordinate transformation from the Cartesian coordinates, so just the atomic positions that are then known. And now you can extend this to very large systems, because for each atom you just add one more line. So you evaluate one more neural network, making this method applicable to thousands of atoms. So this second generation of machine learning potentials therefore is now applicable to large condensed systems. And of course, there are not only high-dimensional network potentials that they introduced in 2007, but in the meantime, many other methods have been introduced. For example, Gaussian approximation potentials by Rajani in 2010, or spectral neighbor analysis potentials by Aidan Thompson in 2015. Moment tensor potentials by Alexander Shapeyev, and Ralph Krauss introduced atomic cluster expansion. Of course, there are many more, so it's possible now to have a comprehensive list of all available machine learning potentials. And I think it's safe to say that second generation machine learning potentials are nowadays the dominant type of machine learning potentials for atomistic simulations. Still, there is a limitation. And this is obvious truncation of the interactions at the cutoff rates. So for some systems, there might be long-range interactions like electrostatics, which are important and should not be truncated. And this is now possible to include this in the third generation of neural network potentials. So the total energy then would be a sum of short-range energy, which is the energy of the second generation, basically, which I've explained to you before, which is shown here again. And then, as a second ingredient, there's an electrostatic energy. And this is based on a set of replicated atomic neural networks. But this time, these atomic neural networks do not produce atomic energies as a function of the chemical environment, but atomic partial charges trained to the DFT charge distribution. And these charges can then be used to compute the long-range electrostatic energy without truncation, and together with the remaining part of the energy represented by the short-range part, then this yields the total energy of the system. So also here now, several alternative methods are available, and including electrostatics and machine learning potentials is nowadays a very active field of research. Still, there is another physical limitation in this inclusion of the electrostatics, and this is if you have global effects in your system, in that the global electronic structure and global atomic structure of the system is important for local bonding. And this is addressed in the fourth generation of neural net potentials. I would like to illustrate the problem here using a very small organic molecule like this, for example. And now, please have a look at this red oxygen atom, and at the opposite end of the molecule there is some arbitrary functional group X. And this X is so distant that it is outside the local cutoff radius of this oxygen atom. So, in principle, the local machine learning potentials of the second and third generation, the properties of the oxygen atom, atomic energy, or atomic charge are independent of the nature of X. And now if we make some choices for this functional group, like an amino group or protonated amino group, and perform DFT calculations for that, then we see that the charges for the same geometric environment are different. Yeah, this is because of long-range charge transfer occurring in this molecule, and this would be then contradictory information for training machine learning potential, and therefore only very inaccurate potentials will be obtained. We can further continue playing this game by selecting more different functional groups, and it's getting even worse. So this problem has been recognized already some time ago by the group of Stefan Dicker in Basel, and he proposed the first fourth generation machine learning potential charge equilibration neural network technique, SEND. And the idea is here to have a second-order Taylor expansion in terms of partial charges of the atoms and the classical Coulomb energy. And this scheme here, this looks very similar to the electrostatic part of the third generation machine learning potential, but there is a difference. This difference is that the charges are not directly the output of the atomic neural networks, but instead the charges are obtained in a global charge equilibration scheme, making the charges depending on the entire structure of the system. And this charge equilibration relies on local atomic electronegativities, which are instead represented by the neural networks. And this allows now this machine learning potential to provide charges which also depend on distant changes in the molecule. So now we joined the forces with the critical group to combine our methods, because the SEND approach works best for ionic bonding to develop a generally applicable fourth generation machine learning potential. And there are changes with respect to both ends and system methods. Yeah, so compared to SEND, we have a modified string now, because the total energy is not our target anymore. The total energy is instead the sum of short range and electrostatic part again. Instead, now we aim for correct charge distribution description in the system by aiming for the atomic charges. And then the second generation machine learning potentials need to provide consistent short range energies. So they get also the atomic charges as additional descriptors to also include the effect of this long range charge transfer. And this now provides us with a very general method applicable to all types of bonding systems, like ionic systems, covalent, metallic bonding. We have long-range electrostatic interactions, flexible charges included. We can describe non-local charge transfer, and the method is also applicable to multiple charge states. So this is what the final scheme of fourth generation neural network looks like. So it's a bit complicated, but in the end, the left blue part is essentially the SEND approach, but with a different training scheme. So we aim for the charges, not for the total energy. And the right-hand side is the short-range second generation neural network part, with the additional charge information provided to the short-range atomic energies for consistency. And then we can again combine the electrostatic energy and the short-range energy here to the total energy of the system. So coming now to some applications, I don't have time. I will focus on the concepts and particular applications, but I still would like to give you a flavor of what can be done with these machine learning potentials. The second generation machine learning potentials have been developed first using silicon, kind of fruit fly system for material science potential development, and then we have looked at different other types of materials like carbon, sodium as a binary system, and then zinc oxide, also including electrostatics in the third generation potential here. And then we extended this to surfaces and also to molecular systems like water clusters, protonated water clusters, supported structures at surfaces, and then liquid water, electrolytes, and interfacial water for solid-liquid interfaces first at metals, and then also oxides, surface dynamics, hybrid materials like metal-organic frameworks, and alloy clusters, confined water, and then also lithium manganese oxide as an important lithium intercalation compound in cathode materials of lithium-ion batteries. So, as an example, I would like to give you just some idea how this works for this lithium manganese oxide. This is a collaboration with Peter Blech and Klaus Thal, and this work was carried out by my PhD student Marco Nicolas. So this lithium intercalation compound, lithium manganese oxide, is very interesting because you can incorporate and remove lithium without changing the oxide backbone structure. This not only makes it interesting as a battery material, but also for catalysis, because you can tune here the electronic structure. Because for charge neutrality, for each lithium ion that you incorporate, you reduce one manganese 4 to a manganese 3. And this is also what makes the system very challenging, the electronic structure point of view, because the manganese 4 ions have a perfect octahedral environment, while the manganese 3 shows the untethered distortion. And this cannot be described correctly by GGA functions and DFT, so the trouble begins already at the reference calculations for training potential. So to overcome this problem, we had to use a hybrid functional P0R developed by Peter Blech in this case. And then we constructed a training set for bulk lithium manganese oxide, water, and interfacial structures. And then they get the root squared errors of a typical order of magnitude of 1 to 2 millieV per atom, and for the forces about 100 millieV per atom. And then we validated the potential not only by looking at the errors of the energies and forces, but also by looking at some physical properties of bulk lithium manganese oxide. And one interesting property that this material has is that because of the alignment of the antenna distorted octahedra, at low temperatures it's an orthorhombic structure, but if temperature is increased, at room temperature there's a phase transition and a cubic structure is obtained. And here you see our simulations for different supercell sizes, and also the average cubic lattice constant. And you can see here that we can reproduce this transition very well, and it converges also as a function of the supercell size. If we now zoom in and look at the lattice parameters, then we see that at lower temperatures we have for these three orthorhombic lattice parameters rather slow, few transitions. At higher temperatures we have faster transitions. And we can further understand this by looking at the individual octahedra. And here you see the three diameters of such an octahedron. And you see here, this is the antenna distorted one, so it's manganese 3 different diameters. And then here's the orientation attempt. This fails at this temperature. But then you see something very interesting happening. And this is the antenna distortion. And this means that in principle, we should have here electron transition, so we form a manganese 4. And how can this be? Yeah? We have no electrons in the machine learning potential, so that could be terribly wrong. Yeah, so we have to ask ourselves, can we trust it? And we had to develop a scheme to confirm that the number of electrons is conserved and that the number of manganese 3 in the system corresponds exactly to the number of lithium ions in the system. So the question can be directly identify spin and oxidation states here. And in principle, this is possible. Here are two simple order parameters, the breathing mode and the antenna mode. And if we look at all our atomic environments, we see that for both of these descriptors, we split all our manganese atomic environments into two groups. And this made us confident that this can also be done with the machine learning approach, so by modifying our neural network, so that here now atomic spins are predicted as a function of the environment. So we can also analyze based on the structure, the electron structure. And that this works as shown here for increasing content of lithium. So you see here purple, the manganese ions, manganese 4 and manganese 3 is shown yellow, and green is the lithium. And the number of lithium ions always in this projection of the unit cell always corresponds to the number of manganese 3. So this works very well. So to wrap up this, the first generation of neural network potentials is applicable to low-dimensional systems only. Then the second generation allowed to extend it to very large systems, making use of short-range energies, making use of the concept of locality of a major part of the atomic interactions. Long-range electrostatic interactions are included in the third generation, and global effects like local charge transfer in the fourth generation. You still see that here on the right side, there's still some white space, and there's one thing missing. I don't have the time to talk about this in detail here, but this is the spin. Yeah, because none of these descriptors are spin dependent, so we could not distinguish, for example, ferromagnetic and antiferromagnetic phases. But this is also possible by using modified atom symmetry functions. So all these generations can also be applied to magnetic systems. So neural network potentials fill a gap in the toolbox of chemistry, physics, and material science. I've just given you a brief overview of one application, but there are many more where neural network potentials have successfully used. So they help solving problems. And finally, I would like to thank some funding institutions and computing centers who supported this work, my group for all the help, and you for your attention. Thank you very much.
Thank you. Anyone to ask a question?
Thank you. Thank you for this great presentation. I would like to ask, what is the accuracy of prediction? You know, like maybe in terms of kilojoules per mole, or something, with respect to the actual values.
Yes, that's a very good point. This is, of course, the critical aspect, because the main motivation was to have an accurate representation of the potential energy surface. Well, I'm always thinking in EV, that's just because I have a physics background, so the typical goal is to reach an accuracy for total energies with respect to the reference electronic structure method of about 1 milli-electron volt per atom. Yeah, so why per atom? Because of course we need to compare the accuracy in a size-consistent way for different systems. If we double the system size, twice the same system, of course, we also have double the error. But most important is in chemistry and material science always energy differences, and here errors cancel like they do also in DFT. So the factual accuracy is much better. And for the forces, it's about 100 MeV per Bohr. That's just the typical error.
It's actually less than the thermal energy, right, at room temperature?
Yes, much less. So thermal energy would be 17 MeV, so it's about
1 over 40, 0.025, I think, EV.
Yeah, it's about.
The reason I was asking this is, would it be possible to apply these techniques? I know, some researchers, some groups are using this in molecular biology. To, for instance, compute binding energies of ligands to proteins. Would it be possible to apply these techniques, or different techniques, would be required?
There are two different ways how machine learning potential could be applied for this. One is molecular dynamic simulation, like you do with a force field, for example. That would be our approach. Or one could also have a big data approach. That's also possible with machine learning, where you learn from similar molecules, where you know the data for the binding strength, for example, already, and try to conclude from this what the binding energy of a similar molecule might be. What the challenge is here for our approach is that in biomolecules, for example, you have a very large diversity of atomic environments. And this makes the mapping of the configuration space for training machine learning potential very costly. But still, there are groups working on that, and there's progress. So going in the direction of a machine learning force field for such applications, that's ongoing work looks very promising.
Yeah, and also the ensemble would be different, right? In biochemistry, one would use physiological environment, where there's, as you say, lots of water molecules. And also maybe NPT, kind of ensemble, I think would be more.
It's NPT or NPT, that doesn't matter, because you can just replace your favorite potential by machine learning potential. Now you can run all types of simulations.
Okay, thank you.
Thank you for a very nice talk. So I have a question, because somehow in your presentation, over time you are using the kind of scheme of feed-forward neural networks. And would it be possible to describe time-dependent problems with usage of recurrent neural network that has a finite memory of history of previous state? And could you make a comment on that?
Yeah, so we are using feed-forward neural networks as the main ingredient for our potentials because this is the tree of methods that we are developing. So we are including more and more physics with the third and the fourth generation. And for this purpose, feed-forward neural networks work very well. Of course, there are many other different types of neural networks and many other classes of machine learning algorithms which work equally well. So this is also possible with the recurrent neural networks. So we are not working on these time-dependent phenomena, but as far as I know, there's also work going on with machine learning in this direction. But I'm not an expert for this, so I can't tell you what the precise state of the art is.
Okay, I see. Because I know that, n-body problems in quantum mechanics can be also somehow reproduced fully by neural networks. So in that sense, but the problem is that this time dependence, because basically if you have a recurrent neural network, probably you can represent any algorithm by performance of recurrent neural network. So this would be an open hypothesis. If you can represent any physical process by a recurrent neural network, that's a kind of open question. So what's your view?
Yeah, I would have to think about it. So since we are not working in this field, it's very difficult now to spontaneously speculate about this. There are so many applications of machine learning potential, so I'm surprised every day what can be done with that. So I would not be surprised if this is possible.
Okay, thank you so much.
Thank you very much. I wonder the properties of the dimensions. Is there any, for example, as a parameter, long range or short range? Is there another dimension which cannot be added to neural network, or all dimensions can be applied or can be added to neural network?
So the question is what do you mean by dimensions here? So because these machine learning potentials are nowadays very high dimensional in the sense that you can include very large numbers of degrees of freedom of many atoms, so tens of thousands is no problem. What this short range and long range more refers to is the physics or the physical phenomena that can be described. So like long-range electrostatic interactions or dispersion interactions are somewhere in between the short range and the long-range region, or these global phenomena, so that you can only address with fourth generation schemes. In terms of the physics, there is certainly still room for improvement. Magnetism is another example for that. But in the terms of dimensionality, I think we have reached a lot already when we can deal with. I think the largest simulation we ever did is 500,000 atoms. Others did even larger. So I think we have reached a very satisfying state here already.
Thank you.
Any more questions and comments? Okay. Dr. Behler, we would like to thanks for your speech.
Thank you very much.
Good night. The second speak is physical layer data communication security exploiting quantum properties of the photons. Orkun Hasekioğlu, TÜBİTAK. Yes.
Değişiyor mu? Uzak mı geldi? Değiştirmesi lazım. O değiştiriyor. Yanlış şeye basıyormuşuz. Okay. Okay, can I start? Okay. So the title of my talk is Physical Layer Data Communication Security, Exploiting Quantum Properties of Photons. This is going to be actually a summary, of a book chapter that we had written. Can you hear? Ses geliyor mu? Geliyor herhalde. Belki biraz yakınlaştırayım. Yes, okay. And also, we had a workshop about a few weeks ago in Mokyo on post-quantum cryptography that was sponsored by NATO. This is going to be basically a summary, of these two efforts. This is, I would say, fundamental physics in action. As we all know, Alan Aspect, John Clauser, and Anton Zeilinger, they were awarded 2022 Nobel Prize in Physics for their experiments, on entangled photons and establishing the violation of Bell inequalities. This is what I'm going to talk about is exploitation, of basically Bell inequalities and its application in actual communication systems to achieve physical layer security. Okay, this is going to be an overview of my talk. This is a longer summary, but I think I'll be able to complete this part of it. Quantum key distribution is an important application of quantum technologies, entanglement and superposition properties of photons. So I'm going to overview the standards, network layers related to quantum key distribution. And then quantum random number generators are also an important part of physical layer security and quantum key distribution protocols. That's also based on quantum properties of particles. This is the part that I'm going to talk about. The next part would include quantum information theory highlights and analysis, correctness and security of these protocols would complete the entire picture, but that I think we don't have enough time to cover all of these topics. Quantum secure communications is really an interdisciplinary subject. It covers a broad range of sciences, including information science, physics, engineering applications, Shannon information theory, as well as quantum information theory, complexity theory, and many other fields. So it's at the intersection, of all these different scientific areas. The secure communications that is based on the principles of quantum mechanics, it's one of the mature and commercialized applications of quantum technologies. There are many other applications of quantum mechanics, like quantum computation and others that we have been discussing in this conference and other places. But this is, I would say, the most mature and it's already being commercialized application of quantum technologies. And the security in this kind of an application it's inherent, it's ensured by the basic laws of physics and also postulates of quantum physics. In quantum secure communications, two of the major postulates, usually of quantum physics are exploited. This is the superposition principle and quantum entanglement. Superposition principle is basically leads to the uncertainty in measurement in non-orthogonal basis. This is in the literature referred to as prepare and measure techniques, because you are preparing a particle, let's say in this case a photon, in a certain state, and then you are making a measurement. So these, if you want to classify, these communication techniques, first one would be prepare and measure. That would be based on the superposition principle, and second one would exploit the entanglement property of particles. So entanglement, as we all know, it's a non-classical statistical correlation, basically, in the properties of two or more quantum particles. Well, these properties could be their spin states of electrons, or maybe polarization states of photons, or ground and excited states of atoms. This is what actually Einstein had referred to spooky action at a distance, in the famous EPR paper in 1935, that seemingly two particles, no matter how far they are, would affect, once you make an observation on one of the particles, the particle A, it would make an instantaneous effect on the state of the second particle, no matter how far they are. So this is the property that we'll be exploiting in secure communications. Just to give you more information or more explanation on the superposition principle, this is on the right-hand side we see the Bloch sphere. Any qubit basically that we could represent as ket psi equals alpha ket 0 plus beta ket 1, where alpha and beta are complex amplitudes, could be represented on this Bloch sphere as a point, on this Bloch sphere. So both quantum computation and also quantum communication consist of manipulating this qubit using operations, gates on this qubit, and moving this basically this qubit on the Bloch sphere. That's the whole idea behind quantum computation and quantum communication. So a qubit, in this sense, is a superposition state of these computational bases, what we call computational bases ket 0 and ket 1. So when a measurement is made on this particular qubit, the technical term is collapsing. The state of the qubit collapses to one of the basis states, either ket 0 or ket 1. So it would collapse to the ket 0 state with probability alpha magnitude square. Since alpha is a complex number, it's the magnitude square of this value would be the probability of measuring ket 0 state, and likewise magnitude square beta would be the probability of measuring the ket 1 state. So this ket psi is called the wave function. It reflects the state of the qubit, and in theory, any information on the quantum state can be obtained from this wave function. So it's a very basic property or basic entity in quantum mechanics. So information is encoded in this state of these superposition states of qubits. So based on how we position this qubit in the Bloch sphere, for instance, if we want to encode the one state, we could position on the z direction, positive z direction, on the Bloch sphere, and that qubit would represent basically one state. And if you'd like to encode 0, for instance, information, the minus direction, minus 1 direction of in the z vertical direction would represent a ket 1 state of this particular qubit. Okay. So these qubits, encoded with particular state, encoded with particular information, can be used in symmetric key encryption. Symmetric key encryption is, let's suppose we call Alice and Bob. Alice is the transmitting party and Bob is the receiving party.
let's suppose Alice has a plain text that she would like to encode or encrypt using a cipher, using a key. And Bob, likewise, in the scheme of symmetric key encryption, would typically have the same exact key as Ali says, and would decrypt the ciphertext. But the problem over here is the secure distribution of the key. Let's suppose there is another party, Charlie, preparing these keys, that would distribute these keys to Alice and Bob. The problem is how you would distribute these keys to Alice and Bob, making sure that there's no eavesdropper on this particular key. Because key is the most important component of symmetric key encryption. Once the eavesdropper, or what we call Eve, has an access to the key, then she can easily decrypt the message. So this is the general scheme. And as we mentioned, this key can be generated and distributed through what we call quantum key distribution protocol. And there are actually networks of this, because in a networked scheme, for instance, you don't have only two parties. It's not usually point-to-point communications. It is a networked, in a networked environment, you'd like all of the parties, participating in this communication would share, the same key. So these key distribution protocol is usually implemented in a networked situation. And quantum random number generators also is an important part, as we are going to see, of these QKD protocols. So again, the general scheme of communication between Alice and Bob. Alice as a plain text, and then there's an encryption algorithm. And according to this encryption algorithm, Alice encodes the information on a quantum state, and then this particular qubit encoded with this information is transmitted through a quantum channel to Bob. A quantum channel could be an optical fiber, or in certain applications could be free space. But we also need to implement securely these protocols, a public channel, a classical channel. Classical channel could be internet or telephone network. As we'll see, almost in all cases, one would need both of these channels. A public channel that is accessible by anyone, including Eve, and also a quantum channel, similarly, that's also accessible to Alice, Bob, and Eve, outside intruders. Okay. Just like conventional communications networks, these are also quantum-based key distribution networks, also have layers, very similar to the OSI layer classification or TCP/IP layer classification. We have a physical layer, data link control layer, network transport, and application layers. And the actual quantum key distribution algorithm is implemented typically in the physical layer. So that was the reason why we call this physical layer security. Physical layer is the actual medium, where the information is transmitted. The quantum key distribution and quantum communications is so much, well advanced that nowadays even a standards organization, including International Telecommunications Union, ITU, ETSI, IEEE, they have their own working groups to develop standards, how to implement these. Because there are already quite few products in the market, and we would like to make sure these products are all secure and safe, and also they are compatible at the same time with each other. So all these organizations, and as Bilgem also from TÜBİTAK, we are participating in these standards organizations, and we try to contribute, to these standards that will, I think, be finalized, in the very near future. So in this standards protocol, this box, where we call quantum layer, includes all the functions, of generating keys, encoding qubits, and this general, diagram also depicts, how this box, quantum layer communications box, is interfaced, with the other layers of the protocol. So this is a typical QKD system, components of the QKD system. As we mentioned, there is a sending unit, transmitting unit, which we called Alice, and also there is a receiving unit, which we called Bob. There is a signal source. Signal source is basically the information. It represents the information that would be transmitted to Bob. And the modulator is where this signal source is encoded, on the quantum particle, in this case photon. And then all of these protocols, basically, they include a random number generator as well, and control electronics, to control the modulator, the signal source, and a random number generator. On the receiving side, again, this information, some of this information is classical bits that is transmitted through a classical channel, and also the qubits, are transmitted through a quantum channel. On the receiving end, we have a signal demodulator, again a random number generator as part of the protocol, control electronics, and detectors. So this is as depicted by the European ETSI, European Telecommunications Standards Institute. This is a general framework for a QKD system. Now let's look at some applications, some details. Like in this particular application, the previous diagram was a generic depiction. But in this particular example, we use, again, we have these random number generators, control electronics. But now we, the random number generator dictates, the phase, of, this is a Mach-Zehnder interferometer that's used to encode, the state of the photon. And for the phase modulators, basically, and together with the Mach-Zehnder interferometer, make sure, that the state that you'd like to transmit is encoded on the phase, in this case, of the photon. And similarly, in the receiver side, we have a Mach-Zehnder interferometer now to demodulate the received state of the qubit. This is another example of a QKD system and its components. Now it's based on, the previous one was based on prepare and measure technique, where we prepare state of a particular photon. In this case, the state encoded being the phase, of the photon. Now this is another example that uses an entanglement-based QKD system. As we see over here now, in this case, we have an entanglement source. It generates two photons that are entangled, and these photons are transmitted through a quantum channel, which is a fiber, in this case, and related electronics, including Bell inequality measurement circuits and detectors are also involved, because you need to make sure that when the entangled pair of photons are generated, there's no interception, and that interception is detected through Bell state analysis. We have, again, avalanche photodiodes, to receive and detect single photons, and FPGAs for implementing the actual protocol. So this is an example of an entanglement-based QKD system. As we said, in terms of the network architecture, the quantum layer in all these protocols, the generation of qubits, encoding the qubits, the random number generation. We are going to see other post-processing, which we'll call key distillation. All of these are implemented in this in the quantum layer. So a typical QKD protocol, both including prepare and measure technique and also entangled photon technique, it includes two parts. One is the generation and transmission of the qubits that represent the Rove key. We call this Rove key because that's not the actual key that Alice and Bob would use eventually. These keys would be sifted, in other words, using classical post-processing. Only part of these keys, Alice and Bob would use. So it would include a Rove key generation and qubit transmission part. And also, the second part of the protocol would include always a classical post-processing, where we ensure Alice and Bob has the actual secure key, safe key that they would use in encryption and decryption. So that's called the symmetric crypto key. As we said, there are two kinds, major kinds of quantum key distribution protocols. One would use prepare and measure approach that would exploit the superposition property. In this case, Alice would encode a string of classical random bits in a non-orthogonal or orthogonal quantum states of photons. Like non-orthogonal meaning she could pick, for instance, the eigenvectors of x and z Pauli operators. They would represent non-orthogonal orthogonal basis. And then Bob would receive these qubits and performs measurements to produce the Rove key. The typical example of this is the BB84 protocol that was invented by Benet and Brassard and AT&T Bell Labs at the time. And as the name indicates, this was invented in 1984. So this shows how far, back the use of quantum technologies go back to in the application in communications. And the second would be entanglement. Again, Rove key data transmission is through the entanglement property of the qubits. And this would entail basically generating the entangled photon pairs and then using Bell state measurements to ensure that there's no interruption or there's no intervention in the communication. Usually in practice, instead of the Bell state measurements, people would use more equivalent to Bell state measurements, but other protocols that are easier to implement. One of them is the CHSH protocol. The name John Clauser, you see over here, is one of the Nobel laureates. I mentioned, in the beginning of the talk. He was the person, actually, when he was in the US, the first person who demonstrated non-local, non-classical correlations in two qubits that are situated, far apart. So this whole story actually started with John Clauser, and then continued with Bell and others, John Bell and others. So typically, one would use this CHSH protocol to verify the non-interception, of the qubits by an eavesdropper during the transmission. This is called E91. Arthur Eckert in 1991 was the first person. He's now in the UK. Who has shown that entanglement could be used for secure data communications. So after his name, this protocol is referred to as E91. Here's a list of major QKD protocols that have been introduced since 1984. As I mentioned, all of these protocols, they are based on two types of approaches. They are variations on these approaches. One was the prepare and measure approach, as we said, would exploit the superposition principle of a qubit, and the second would be the entanglement approach. So in each iteration, of these protocols, some safety feature, of the protocol is improved. So this is like a short, maybe a set of, short example, list of examples of such QKD applications. The Heisenberg uncertainty principle over here basically refers to the prepare and measure, because if you measure in non-orthogonal basis, there is an uncertainty, in the measurement. That's why it's called over here Heisenberg's uncertainty principle. So after the key is generated through an entanglement or other means, and we obtain the raw key, there is classical post-processing. What does this classical post-processing do? It involves several stages typically, and it makes sure that the key that Alice and Bob has, they are the same actual key, and also they are distributed in a secure manner. One is the key sifting, the first stage. That's the reduction basically of the raw key, where parts of the key is eliminated that Alice and Bob think that Eve has access to. This is called key sifting. And part of the keys are also, part of the raw key is also used for channel parameter estimation, a quantum bit error rate, basically. The error rate, there's also noise, in the communication channel. And also there are, of course, measurement and other errors. So for in real applications, one would need to estimate the communication channel parameters. And also there are error correction also. This is classical error correction. In a typical communication system, it's possible to add redundant bits. You have your actual data bit stream, but then you can add a set of redundant bits. So in case of an error in the real data, one could use the redundant bits to correct the possible errors that could occur in the actual data stream. And there is also a fourth element, which we call privacy amplification. This is an information theoretical approach where we eliminate the information that is obtained by Eve on the key. So these four steps constitute classical post-processing part. In a typical, for instance, BB84 QKD protocol, which is based on prepare and measure, Alice now is the transmitter, Bob again is the QKD receiver. There is a set of generated raw bits, raw classical bits, that are encoded on the qubits and transmitted to Bob. And then these qubits, these raw data is encoded on the qubits through the use of some bases. In this case, for instance, we use, Alice uses either rectilinear basis or diagonal basis. Rectilinear basis is the basically eigenvectors of the Z Pauli operator. Diagonal basis is the eigenvectors of the X operator. And at random encodes these bits. And then there is the sifting stage where Alice and Bob, they announce both the basis of encoding basis and measurement basis that they have used. If the encoding basis and the measurement basis they match, they select those bits. If they don't match, they discard. Again, there is some loss. In each stage there is loss of the actual raw keys that have been generated. And then there's the key distillation phase, where the channel parameter is estimated, there's error correction is done, and the privacy amplification. The four stages, post-processing stages are implemented. So eventually, out of a long string of raw keys, Alice and Bob now has, as a result of this protocol, a shared secure key. This is how BB84 protocol would work. There are a few ways, of classifying QKD protocols. I'm just looking. How am I doing with the time? Okay. There is first classification. Okay. There's, as we said, the classification we mentioned, preparation and measurement, or entanglement encoding classification. Another classification one could look into is device-independent or device-dependent protocols. Device-independent protocols would mean even the Eve would know the particular transmitter or receiver structure, the particular receiver and transmitter structure, and the protocol is known by Eve. Still, the protocol works securely. These are referred to as device-independent protocols. Another way to look at these protocols is one-way or two-way, bidirectional or single-directional qubit transmission. And the fourth way that we have not seen so far, but I'm going to do some explanation on this also. Discrete variable or continuous variable qubit encoding and decoding. In discrete variable QKD systems, one would use single photons. The information is encoded on the properties of a single photon. And also this would require, of course, single photon generation and single photon detection, equipment hardware. But in the case of continuous variable, as we'll see, the one would use a laser, a classical laser beam rather than a single photon. And the information is encoded on the, because laser beam is basically an electromagnetic wave, so it has quadrature components, and the information is encoded on the quadrature components of the laser beam. The continuous variable, the advantage of continuous variable QKD is it's possible to use already available equipment that one would use in optical communications, fiber optics communications. It's basically the same equipment one would use. So it's in practice, this continuous variable systems are getting more and more popular. So discrete variable QKD, as I mentioned, one would use a single photon, and the information is encoded, and there are discrete states or discrete data that one would like to transmit, and the information is encoded in the quantum states of a photon. The quantum state could be the polarization, the orbital angular momentum, or as we have seen, the phase, any property of the photon could constitute the state, of a photon where we could encode this information. And the encoded photons, then they are received by Bob. They are, in this case, received by single photon detectors. These are avalanche photodiodes, could be popularly used, or nowadays the photo detectors, based on superconductivity, they are much more sensitive, close to 100%, 98% quantum efficiency is possible nowadays with these superconducting detectors. It's based on the photon. When the photon is hits, on the surface of a superconducting surface, the heat that's generated by the photon basically it changes the resistivity. So by using the resistivity, changing resistivity values, one could detect a photon. That's the most efficient way of single photon detection. And there are again quite few well-known examples. They're all based on, as you said, either prepare and measurement or entanglement, but these are the varieties of different kinds of discrete valued QKD systems. In the case of continuous valued QKD, one would, as we said, encode the information to be transmitted on the quadrature components. We call X1 and X2 components of the electromagnetic field of the photons or the laser. These are X1 quadrature components. These are the components in the optical phase space. And when Bob receives this laser beam encoded on and the information on the encoded photons, he uses coherent or coherent homodyne or heterodyne detection. These are techniques used in optical communications, so equipment is readily available, to do these measurements. When it comes to the security of QKD protocols, how secure are these protocols? There are two basic approaches to this. One, there is the information theoretical security. It's always possible to compute, the mutual information that Eve would obtain by measuring the qubit using quantum information theory, or even in certain cases classical information theory. But in the real applications, the level of security is usually is less than this. That's because there could be certain loopholes, in the, as we are going to see, in the hardware, in the device, in the software implementation. The implementation is usually never, as exact, as defined in the actual protocol. And this is called implementation security. In implementation, because of the loopholes, there are always, unsecure means, that Eve would use to intercept this communication. I'll show these things in a separate slide, so I'm going to skip these for the sake of time. So this is a list of security attacks that Eve can implement on the communications channel. The security attack could be either to the photon source, photon detection, or encoder and decoder of the communication system. And it's all for the purpose of gain information on the key. So all these attacks would be possible. I'm not going to go into the details of this, but there are. This is a quite involved research field to understand security features and compute and analyze security characteristics of QKD systems. Are the QKD protocols, are there any implementations of this? Yeah, yes, there are. There are many test beds worldwide, actually, in Europe, in Japan, and the most recent one is the Chinese MICUS satellite system, where a low Earth orbit satellite transmits an entangled pair of photons to two stations on Earth, two locations, and then going through the Bell state analysis and other security checks, one could distribute entangled pairs and consequently a secure key to two parties. So the objectives of all these Chinese and Singapore experiment and other test beds is to have a secure network worldwide, a global network where you could ensure secure communications from any point A to point B. That's the whole purpose. And that's guaranteed by the laws of physics. Yeah, I'm not going to go to the details, but these are all variations of the BB84 of the different DV QKD, discrete valued QKD protocols. Like for instance, in B92 version of the BB84 protocol, instead of four, non-orthogonal bases, this is a version of it where it would be possible to use two non-orthogonal bases. Or in the case of the six-state protocol, as we remember, the block sphere that we have seen at the beginning of the talk, it has six antipodal locations. So it's possible to use all these six states, instead of four states to transmit information at a higher rate. And there are other versions, like SARC-04 that's implemented in the Tokyo quantum key distribution network that would eliminate attacks, based on photon number splitting, PNS attacks, So there are all versions of this particular protocol. Okay. This example, which we call COV, coherent one-way protocol, was actually, the reason I'm showing this is this was implemented at TÜBİTAK on an optical table using standard optical components. In 2014, it uses the source now is attenuated, laser source, so that you make sure, the photons are coming, individually, are transmitted individually. So it encodes the information on the time bins, transmitted. So 0 and 1 bits are encoded in this way. Again, you have a quantum channel and a classical channel. Okay. So as we said, in the continuous variable quantum key distribution, as opposed to discrete variable quantum key distribution, one would use lasers instead of single photons. Lasers and also homodyne and heterodyne detectors. And the information is encoded on the quadrature components of the laser beam. This is a typical implementation of such a protocol. There is a laser source and encoding and quantum channel is in this case a fiber channel and the homodyne detector. The commercialization studies of continuous wave and QKD and discrete valued QKD, there are quite few commercial products nowadays, and even some of the commercial organizations, like banks, there are the implementations for some time are there. Banks and other places, besides these test beds, other government organizations use QKD protocols. There are suitable commercialized products, both in continuous valued QKD and also discrete valued QKD. I would like to say a few statements on quantum random number generators, because this is together with QKD, quantum random number generators also exploit quantum properties of photons, typically photons, but it could we could use other quantum systems besides photons, but in this case photons. The number random generators can be classified as pseudo-random number generators. These are basically, they depend on deterministic algorithms. They appear random. I mean, if you look at the autocorrelation function, they appear random, but they are deterministic. They typically use shift register sequence and other deterministic algorithms. So if one would have access, if Eve would have access to the particular algorithm, it would be possible for her to produce the exact random number sequence, sequence in this case. There are also true random number generators. These are still classical. They don't use any quantum property, such as the terminal noise on a resistor, atmospheric noise. One could sample all these noise sources and come up with random numbers with a random number generator. But as opposed to all of these, quantum random number generators are the randomness is generated by the laws of physics. Like, for instance, if you toss a coin, head or tail, apparently it's a random number source, but it is due to the lack of our detailed information on the actual physical system. If one would know the details of all the position and also momentum, of the initial conditions of the coin, in principle, it would be possible to compute, whether you would deterministically, whether you would obtain head or tail. But in the case of quantum random number generators, the randomness is due to the laws of physics. You don't have any means actually computing the actual numbers. It's not based on the insufficient information that one would have. Rather, it's because of how physics work. And one example of this could be, let me give some examples. For instance, the decay time of an isotope, the beta decay. This time is a random source, and the randomness is guaranteed by quantum physics. And similarly, beam splitters. A photon hitting a beam splitter, whether it will be reflected or transmitted, that's also related to quantum physics. That's also a real random number source. Just like the QKD, a random number source, even if it is a quantum random number source, we need to do a post-processing. For true randomness, the source should be uniformly distributed and statistically unpredictable. In other words, future data, past data should not have any information on the future data. It shouldn't be possible to have any information or compute the future data based on past data. So to ensure this statistical characteristic, one would make sure the data is uniformly distributed and statistically unpredictable, uncorrelated. So this would require post-processing. And this diagram basically summarizes what I just said. Okay, so skip this. Okay, so I think I've taken much longer, than I should have. But if this would have been a real, like a coursework or class, or longer, if you had a longer time, then would describe maybe some quantum information theory highlights, some minimum information on how information is defined in quantum systems, and how quantum channels would have, because just like classical communications in quantum systems also, the source has carry some information, the channel has quantum information theoretical capacity. For full understanding and analysis of such systems, one would have to know some quantum information theory. And also, we could, using these tools, we could analyze all these protocols, and we just talked about, BB84, E94, and analyze and do apply CHSH tests and best state analysis. Okay, and also just before closing, I'd like to mention teleportation. I didn't mention much over here. It's also an important component of quantum networking and quantum communications because of the non-cloning theorem. In a typical classical communication system, one could easily the the stream, of bits, you would like to transmit. But in the case of quantum communications, because of the no-cloning theorem, it's not possible to copy a qubit and retransmit, So one uses, and there are also now physical implementations of this, to teleport. And this protocol is called entanglement swapping. One could use entanglement swapping even on a chip. You could, like one part of the chip to transmit a qubit. All these things are implemented and they are possible. And another important maybe aspect of this would be implementation of all these protocols using linear optical elements. Like lenses, mirrors, polarizing beam splitters, delay elements. These are all linear optical elements. Apart from a few particular cases, it would be possible to implement all these. There are, in details, you would need some nonlinear optics and some electronics, but in general, most of these protocols, it would be possible to use linear optical elements, to implement either on desktop or on a chip, So all these things are possible. Okay, so thank you for listening. Sorry for keeping you, longer than planned, but.
We would like to thanks for your good talk. Any comments or questions? Yes, Şemsettin Hocam.
If the Eve is listening all the time, and how would you transfer the key from Alice to Dabab?
Okay, so like in the case of, for instance, entanglement-based protocols, E91, a CAD protocol, using statistical analysis, of the qubits received, Alice and Bob, basically implementing, Bell state analysis, they could infer, whether there has been an eavesdropping or not. Like in CHSH test, for instance, they do some correlation measurements. If it is below 2, that particular correlation, then they say, there has been a measurement by Eve, so this, entanglement has been destroyed. But if it is 2 times square root of 2, there is an equation that I have not described over here. So if the correlation, is above 2 and below 2 square root of 2, then Alice and Bob, would infer, there has been a non-classical correlation, quantum correlation. So there's no, eavesdropping on the transmitted qubits. So it's basically using Bell state analysis.
You're using the Bell state analysis, but if the Eve is continuously, without interrupting, is the listening?
Yeah. Then they retransmit. Basically.
Yeah, he's listening all the time.
Yeah.
He tapped onto the communication lines or receiver, whatever it is, and continuously is the listening.
Yeah. Well, I mean, then they would retransmit until until they make sure, that.
Until they make sure.
Yeah, there's no interruption.
I see. Okay.
I mean, in the technical analysis, it's easier to describe, how this could be implemented in practice, but roughly, this is.
But also, Alice will not know whether or not the information is compromised by Eve. Only the Bob will know it. So Bob has to communicate with Alice.
No, Alice and Bob, they share, this kind of information. The statistical analysis results they share, until they both, make sure that they have, they have the right, secure key. So both Alice and Bob, as a result of this protocol, they make sure the key is secure. Yeah.
But each time Alice will generate another key, each time it will send different keys, and those keys on the way will be listened by the Eve. If third party sets up another system on the path and keeps
Yeah, but I mean, I would say it's not possible to always intercept, you know, because let's say you are doing this on a satellite transmission. You have the entanglement photons, just like in the Chinese case, you know, the MICU satellite. They are prepared in the satellite and they are transmitted to the ground. So it's not always possible to capture, you know, each one of the photons, right? Entangled photons that's transmitted to the ground.
But also that they encoded the information more than one entangled photons, because most of the photons, there's a probability, are lost on the way.
Yeah, especially in the atmosphere, you know, 1 in a million, you know, typically, once you send the entangled pair, because of the interaction, you know, with the atmosphere, the molecules in the atmosphere, the coherence, you know, is destroyed.
Of course.
But 1 in a million, you know, like these things have been measured of the photon pairs. They reach, you know, the ground without losing the entanglement. And they use coincidence detection, you know, just to make sure, you know, because they need to identify the pairs, you know, of entangled photons. They cannot just, you know, pick, you know, random photons. So they use coincidence detection, and they implement CHSH, you know, tests on these particular entangled photons.
The problem in that communication, since they are encoding the information into a bunch of photons, some of them is arriving to the detector over there, some of them is arriving to somewhere else, for example. Some of them are lost in the atmosphere, of course.
Yeah. So they just pick the ones, you know, that have, because all of these entangled pairs, right, they are basically like one of the bell states.
Yeah, you're right.
You can use one of the bell states. So at the time of measurement, Alice and Bob, you know, depending on what bell state they use, is transmitted. Either they have the same random bit, or you know, opposite random bits. Yeah.
Any more questions or comments? Thank you, Orkun Hoca.
Okay. Okay. So sorry for keeping you, you know, so long. Okay. Okay. Thank you very much. Thank you very much.
Decision is finished.